Okay, in this part of the video, I'm gonna go through problem number 2 and problem number 3. Um, Problem number 2, actually, you will have to find out the answer for these questions yourself. You need to do a little bit of research in order to solve this kind of problem. It's quite straightforward. It's not very difficult or challenging, but you have to do your homework in order to do that. So the first part, it says describe why the endurance limit for steel alloy bar would be different in uniaxial tension compared to endurance limit results obtained from a rotating beam test, the standard test, on a bar of the same material and dimension. So if we have two specimens with made from the same material with the same dimensions, but one of them is tested under tension and the other one is tested under bending. So why the endurance limit is different? So you need to find out the answer to this question based on the fatigue learning pack that is available on our Canvas page. Also, you can make use of the text box that are available from our resource list on Canvas page again, and you can do other internet search as well. But here, for example, as a hint, to just think about how the stress is distributed across the specimen that is subjected to tension and bending. So just think about how the stresses are distributed in both cases. The second question, it says, what effect does surface finish and size have on the endurance limit of a steel component? So the surface finish here and the size of the specimen, they play a very important role in finding out the value for the endurance limit. So it affects the endurance limit, whether the specimen is a standard specimen or a larger or smaller specimen. So this is going to have an effect on the endurance limit, and also based on the surface finish of the specimen. Either it is smooth or just machined or forged, etc. So you need to find out what effect does this surface finish have on the endurance limit. The next problem, or the next question here, it says, how does notch sensitivity alter with the size of notch and material strength? You would have seen in the recorded lecture or the class how the notch sensitivity changes based on the dimension of the notch itself and based on the material as well. So you need to find out more about that. The next question says, describe two processes which reduce and two other processes which increase the fatigue strength of the material. So towards the end of the fatigue learning pack, you will find the processes that kind of increase or maintain the fatigue strength of the material, including surface treatments and so on. So you need to think about this as well. Now I'm going to switch to problem number 3. I'm going to go through this problem as well in this video segment. So the problem says here, the flat plate shown in this figure here is made of ductile plain carbon steel, for which the ultimate tensile strength is given as 629 megapascal. So the ultimate tensile strength of the material is given here. The axial load, you see here, we have an axial load of 5 kilonewton. So the axial load P of magnitude 5 kilonewton is completely reversed. Completely reversed here means that the maximum force is plus 5 kilonewton and the minimum force is negative 5 kilonewton. So F max is plus 5 kilonewton, F min is negative 5 kilonewton. If for the material and configuration shown, the notch sensitivity is given as 0.9. So the Q value here is given as 0.9. Determine the factor of safety for an infinite life. So the factor of safety is required. In this case, also assume that the endurance strength of the material is 0.5 is ultimate. So in this case, we have to find the factor of safety. Looking at the figure here, or the configuration that is given, you'll see that we have two stress risers. One at this pin here, or this hole here, and the other one at this fillet. So we have to find two fatigue stress concentration factors and choose the higher one. The thickness of the plate is given here as 5 mil, and all these dimensions, the smaller width here is 40, the larger width is 70, the radius here of the fillet is 5 mil, and then the diameter of this hole is 20, and the distance between the edge to the center point or the center line of the hole is 20. All these dimensions are required in our case. So you see here we have a larger width is D is 70, as I've shown on the figure. The small width, small d, is 40. The diameter of the hole is 20. The fillet radius is 5 mil. The thickness of the plate is 5 mil. The notch sensitivity was given as 0.9, and the load was given as plus or minus 5 kilonewton. Factor of safety is 1.5, and the yield strength of the material, or the ultimate tensile strength of the material, was given as 629 megapascal. As I said, we have two places where stress is going to be magnified. One at the fillet, or this transition from the small width to the large width, and the other one is at the hole, where we have a hole here, so around the hole we'll have like some magnification of the stresses. So what we're going to do here, we're going to calculate the stress concentration factor for both cases and choose the higher one. On the left-hand side, you see we need two pieces of information in order to find the stress concentration factor K sub T. The first one is the ratio between the radius here of this fillet over the smaller width. The radius of the fillet is 5, the smaller width is 40, so this gives us 0.125. So we've just picked here, or just identified the first point. So we can draw a line here, a vertical line at this point. Then we're gonna choose one of these curves in order to find the value KT. So these curves are capital D over small d. So it shows the ratio between the larger width and the smaller width. The ratio here is 1.75. But here, this curve here, the last curve on the graph is d over d is equal to 1.5. So we have to extrapolate. So again, this is going to be a little bit approximate, but if we just draw here a curve that is parallel to this curve and it's just a little bit away from the curve, with your judgment that this is d over d is equal to 1.75, then this gives you a stress concentration factor is 2.18 in this range. On the right hand side, we have to find the ratio between the diameter of the hole over the width of the plate, which in this case is 20 over 40, 0.5. So we just have identified the first point here. So we have to draw a vertical line, and then we have to intersect with one of these three curves based on the ratio between H to W. H is the distance between the edge to the center line of the hole, which is given as 20 here. The width of the plate towards this end where we have a hole is 40, which is the smaller width actually. Is 0.5. So this ratio is 0.5. Unfortunately, we have a curve here that H over W is 0.5. So we just go up, intersect with this curve, go to the left. It gives us this value of stress concentration factor, which is 2.65. In this case, if you compare these two values, you will find that this value is higher. So we're going to focus on this value, and consequently, we are going to focus on this area here, which is the minimum area, we're going to call it. But after we have found the stress concentration factor, we have to find the fatigue stress concentration factor that we denote as K sub F. to take the sensitivity of the material or the notch sensitivity of the material into account. So the K sub F is 1 plus the notch sensitivity of the material, that is given as 0.9, multiplied by KT, the value that we've got from the chart, minus 1. So this gives us 2.485. Then here, in order to use the Soderberg equation, we have to find both the mean and the reversed stresses. And before that, we have to find the mean and reversed force. The maximum and minimum forces are given, like plus or minus 5 kilonewtons. So the mean force actually is 0 because we have a completely reversed loading. And then the reversed force here is equal to the maximum minus the minimum force divided by 2, which is 5 kilonewton. Because we've considered the stress concentration factor at the whole, so we're going to focus on and use the cross-sectional area around the hole, which is again W, the width of the blade at this point, minus the diameter of the hole multiplied by the thickness of the blade, which is given as 5. The width is 40 and the diameter of the hole is 20, so we have the cross-sectional area here. The mean force is 0, so the mean stress is 0 as well, but the reversed force is 5 kilonewton, so we can calculate the reversed stress. So the reversed stress is the reversed force, which is 5 times 10 to the power 3 Newton, divided by the cross-sectional area, which is 100 millimeters squared. So this gives us 50 megapascal. So we can take these values. Sigma mean is equal to 0, sigma r is 50 megapascal, and then substitute these values into the Soderberg equation in order to find the factor of safety. So this is the Soderberg line equation based on the similar triangles. And then simply we can rearrange this equation to find the factor of safety. So the factor of safety is the yield strength of the material divided by the mean stress, which is 0, plus the fatigue stress concentration factor based on the notch sensitivity and the stress concentration factor found from the chart, multiplied by the yield strength of the material over the endurance limit, or the endurance strength of the material, multiplied by the reversed force, the reversed stress. In this case, S yield was not given to us, so we're going to consider that the worst case scenario is S yield is equal to S ultimate, and also we're going to assume that the yield strength of the material here is equal to 0.5 S ultimate based on the chart in the lecture. So for steels, the endurance strength is equal to 0.5 multiplied by the ultimate tensile strength of the material. It's also here, we can remember that S yield is equal to 0.4 multiplied by the S ultimate for cast iron. So this specifically, this 0.5 is for steels within a specific range of tensile strength. In this case, the factor of safety is equal to the S ultimate, which is kind of the worst case scenario, divided by the mean strength. The mean stress of the material is 0. KF value, fatigue stress concentration factor, is 2.485, and then here we're going to replace the S yield by S ultimate. We're going to replace the endurance strength by 0.5 S ultimate again. Or we do it the other way around. We consider that S ultimate is 2S multiplied by the endurance strength over the endurance strength. These two cancels, and then multiplied by the reversed stress, which is 40. So this gives us the factor of safety of 2.53. So in fact, this component, based on the current material and the current assumption, the current loading, is going to live for infinite life. So this is the end of problem number 3.